Okay, 1.12 is on rules of inference let's see. Rules of inference with propositions. Okay, so some statements are valid, and we just are going to list that they're valid based on what we know. Okay, and then we can utilize those rules from here on out. So rules of inference known to be valid. Okay, rules of inference known to be valid arguments. Okay, so we're going to have the rule, and then we're going to have the name. Okay, the rule and the name. Okay, rule number 1. P, hypothesis P, and hypothesis P goes to Q, therefore Q. Okay. The name of this is called modus ponens. Okay, modus ponens. We have P, and we have P goes to Q, therefore the conclusion is Q. Okay, number 2. Not Q, P goes to Q, therefore not P. Okay, and this is kind of like the contrapositive statement. This is called modus tollens. Number 3. P, just P, okay, therefore P or Q. Okay, so we just have P, okay, and we go to P or Q, the conclusion is P or Q, then this is a valid statement, and we call this addition. We're kind of adding on a Q. Okay, number 4. Okay, P and Q, that implies P. This is called simplification. Okay, number 5, P, Q, therefore P and Q. That should kind of make sense because two hypotheses are being combined with an and operator. Okay, so this is called conjunction. It's a conjunction. Okay, take P, take Q, and then conjoin them. That's a valid statement.
Sorry, Professor, could you scroll up just a little bit? Sorry about that. Thank you, that's perfect.
Okay. Okay, number 6. Okay, if P then Q, if Q then R, that one implies if P then R. Okay, and this is kind of like the transitive property in algebra, but in logic, we call this a hypothetical syllogism. Okay, number 7. P or Q and not P, therefore Q. P or Q and not P, therefore Q. This is called a disjunctive syllogism. Okay. Okay, number 8. P or Q, not P or Q, I'm sorry, not P or R. Okay, P or Q, not P or R, implies Q or R. Okay, this is called a resolution. Okay, let's look at the disjunctive syllogism real quick. Let's see what's going on here. If I have P, Q, okay, not P, well, let's do P or Q first. P or Q, okay, not P, okay, and then Q again. Okay, we have true, true, false, false, true, false, true, false. So P or Q, well, that's true, 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 false. Okay, what's not P? Not P is false, false. Okay, false. Not P, yeah. Is true, true, that's correct. Okay. Okay, false, P is false, false, true, true, right? And we want to do an and statement here. Right? Okay. So we want to do an and statement. Maybe we should do it like this. Okay, P or Q and not P. Okay, does that imply Q? Okay, so let's do the and statement. That's going to be false, false, true, and then that's and, yeah, that's and. True, and then this would be false, right? Okay, and they're saying that this should be equal to, okay, a valid statement. Okay, this implies Q. Okay, well, what is Q? Q was T, F, T, F. So now I want to know, is this valid? Is this valid? Well, the only time I have a true, I end up with a true. The other ones, okay, I end up with false, true, false, false, but we don't care when they're false, and false, false. So I don't end up with any TFs here. Okay, this is valid. Okay, that's a valid argument. Okay, I don't end up, the only true goes to a true. I don't end up with true going to false. Okay, And so it is valid. There is no true going to false. Where all the hypotheses, the only time the hypotheses are true is when P is false and Q is true. Okay. That's the only time that the hypotheses end up being true. Okay, hypothesis true with true. This is a true hypothesis, true hypothesis. So all of the hypotheses are true, and then it goes to a true for the conclusion, so it's valid. Okay, the false ones we don't really care about. They're valid regardless. Okay, for that column there. Okay. Okay, example 1. Okay, use the rules of inference and the laws of propositional logic to form a logical proof of the validity of the following argument. Right? So we're gonna utilize these laws now to find the validity of the argument. Okay. So we have P and R, or R goes to Q. Okay, Q goes to T. And then we have R, therefore T. Okay, so let's try to see if is this a valid or invalid? Is there a case? What we're really asking ourselves is there a case where the hypotheses are all true, but the conclusion is false? Is there a case where the hypotheses are all true, the conclusion is false? And no, that doesn't happen, because we can build a bridge from all these hypotheses using the fact that we know that certain things are valid, and we can build a bridge to get to T. So statements. If we can prove that everything here is true and T is true, if all the hypotheses are true, and then it leads to T being true, regardless of the value of T, then we win. So statements, justifications. Okay, we're building a bridge between what we're given and what we want, the conclusion. Statements, justifications. Okay, number 1, R. Okay, what's the justification for that? It's a hypothesis. Okay, now what do I want? Now I want P and R, or P or R. 2, P or R. Now, if you give me R, okay, then I can get a P or R. those are logically equivalent statements. R or P or R, logically equivalent, logically valid statements. Right? And so we go back to our our rules of inference, and we say, well, which one is this? This is addition, number 3. Okay, you give me P, I get P or Q. Okay, in this case, it's just R. P or R, that's what I want to get because it's right there. Okay, and so we're going to say that's addition from line 1. Okay, put the line number that I'm referencing. Addition from line 1. Okay, number 3. P or R goes to Q. Okay, what is that? P or R goes to Q. That's a hypothesis. Okay, and that now I can just go to Q. Why? Because if I were to take these two, P or R, P goes to Q, then just Q. And that's modus ponens up here. P goes to Q, therefore Q. Well, we just have an or R attached to the P. P or R goes to Q, therefore Q. Logically valid. So this is modus ponens on lines 2 and 3. Okay, number 5. Q goes to T. Okay, so Q goes to T. Where do I get that from? I just pull it out of thin air. Q goes to T is what? Not everybody wants.
A hypothesis?
It is hypothesis. Thank you, Jesus. Hey, where's the hypothesis? It's right there. Hey, it's a hypothesis. And so if I do Q goes to T. If I look at these two now, Q goes to T, then what am I left with? Just T, right? So again, that's modus ponens. And that's on 4 and 5. Okay, therefore, the argument is valid. So we didn't have to even use a truth table on all of this. Okay, we didn't have to use a truth table. We could just go through it like a systematic proof. Okay, let's do one more of these. Okay, example 2. Use a logical proof to establish the validity of the following argument. Okay, if it is raining or windy or both, the game is canceled. The game will not be canceled. Therefore, it is not windy. Okay, so hopefully you can see that this is a valid argument, kind of just in your brain, but let's go through systematically and prove it. Okay, let's let R represent raining. Let's let W represent windy. And let's let C represent canceled. Okay. So what are we given here? Well, we're given if it's raining or windy or both, then the game is canceled. Okay, the only way it's not canceled is if it's not raining and not windy. Okay. Not canceled, the game will not be canceled is the second hypothesis. Therefore, it's not windy, not windy. So let's see if we can justify this using our rules of inference.
I was just wondering, for the first hypothesis, because it says raining or windy or both, wouldn't it be R or W and then or R and W, then C?
Well, let's think about that for a second. Okay, so let's look at a Venn diagram here. So we have raining or windy or both, right? It could be raining. It could be windy, or it could be both, right? Raining and windy. Okay. So okay. But if I take raining, okay, the game is canceled. If I take windy, the game is canceled. So either way, this overlap is taken into account. Does that make sense?
Yeah, okay, thank you.
You're welcome. So I want my statements and my justifications okay, so let's look at our statements and our justifications. Okay, number one. R or W implies C. That's a hypothesis. And not C. This is a hypothesis. Okay. Is there anything that I can do here? Okay. to help me with the next step? Okay, is there any rule of inference that I can use to help me with the next step? Okay, so not Q, P then Q, therefore not P. That's modus tollens. So this would be not R or W. So that's modus tollens. That's kind of like that contrapositive. Okay, modus tollens on 1 and 2. Okay. Now let's go not R or, I'm sorry, and not W. What is that? How did I go from 3 to 4?
De Morgan's.
Yep, De Morgan's. Okay, on 3. Okay, number 5. I really want to get this guy. So I actually have to reverse the order. I have to say not W and not R. And that is just the commutative law. On 4. And then we could say, well, if we have not W and not R, we could simplify that to not W, right? So if we go back up here, okay, there's modus tollens that we used earlier. Okay, and now we want to simplify P and Q, therefore P. P and Q, therefore P. Okay, so P and Q, therefore P. So not W and not R, therefore not W. And that is simplification. Five. Okay. So that should be 1.12.